Good afternoon, everyone. My name is Eop, and I came from New York University in Abu Dhabi. New York University is quite a new university, but we are having emerging research teams, and I belong to one of them. It's a construction research group, and today I'm going to present one of our research work, which is actually ongoing. It's called Using the Rate of Color Evolution of a Point Cloud to Monitor the Performance of Construction Traits. Now, before I go deeper into our project, I want to display this data, which is published by PMI in 2018. It's their annual publication is called the Pulse of Profession. So in this page is the project performance page, which is mainly written for construction. On the second line, they say that 53% of the projects which are under this study were completed on time, which leaves with 47 of them were delayed, which means this can be taken as an example. Still, construction delay is a big issue, and something has to be done about it. So our project is directly related to that. So the objectives of our project is subdivided into three. The first one is identifying activity performance of construction traits. So you can see from the image, most of the tasks that we say on the beam or any schedule involves the outputs of traits, multiple traits, and it's sometimes very hard to track which trait is actually responsible for any delay. So we need to find out which one it is, and our methodology will try to come up with methodology to do that. The second one is proposing an innovative construction data collection method. So as we all know, the current construction methodology on site involves time-taking and labor-intensive construction data collection methods. Mostly collecting them and analyzing them and then putting them for the project management team to give decisions earlier is kind of difficult because it involves time-consuming activities. The third one is, of course, analyzing this data and coming up with decision support information. How do we do that? Now, before we go there, I wanted to say something about color, since our project is highly dependent on that. We were just looking around and we found this interesting. We found this from the textile industry. They use color difference very deeply and to characterize their materials. We thought, like, why don't we just try to bring it to construction and see if that can actually help us monitor construction. However, color is not a very fixed property of material. It actually depends on the, as you can see over there, for light intensity, reflection characteristics of the material, or the observer's characteristics. Therefore, we have to have a method to fix it and to take it as a constant property. That's why we choose to use CILab color space. Yeah, a lot of electronic devices give you RGB color space, but that's actually highly dependent on light intensity. But in a CILab color space, we can differentiate chrominance and illuminance properties, and the L axis can be just taken out, and our project will be depending on the AP plane. Now, these are the three main steps of our methodology. The first one is the as-planned color-based productivity determination. At this phase, we are enhancing or giving more information to our beam data so that our beam data can be related to color of material that we expect. So it's going to be a stage-wise expectation of color that can be acquired from the manufacturer of the material, or that can be done on-site as well within a controlled environment. Once we get this data, we are going to input it on a beam model, and that is going to help us monitor it. However, after the construction is started, we need to generate more data, and then we have to compare it with what we have generated initially. So the second one is just point cloud data processing. Getting a point cloud from the site, it could be using photogrammetry, it could be laser scanning, it could be videometry, or whichever possible method to get a point cloud will be used, and the point cloud generated will be processed, filtered, segmented, and the color property will be extracted. The last one is just equating and comparing these two. I wanted to explain this in an illustrative example that we have done in our lab. So we have built a very short prototype of a column. And before we do that, we prepare this so that we can exercise the first step of our methodology, which involves all the usual information and additional information, which is this one, PAP1, PAP2, and PAP3, which means as planned point 1, as planned point 2, which goes, so this is what we are expected to find out initially and put it on our B model. How do we get those points? This is how we get it. So, for example, we kind of put these two materials. This is what we use for formwork. That's the timber surface. And that is the concrete surface that we expect to get after the formwork is stripped off. Now, we took images of these two in a lab, in a controlled lighting environment and everything. And we converted the RGB color into AB color space, and this is what we have got for that. However, we cannot take all these points and then say, okay, this is what we expect at this stage. We have to have a representative point as a centroid. So we took a centroid of these points, and we took that as a representative. That's why we said PAP. So for the first one, this point, this red dot is called a PAP1. That's a PAP2. The same procedure will be followed for all the steps. And this is what you get afterwards. So we have this four-step construction procedure. We have these 3 points. We cannot get a second one because it's kind of covered. We cannot generate a point data for that one. Now, this distance is the amount of work that we expect to convert the formwork face, the formwork color, into the concrete color. And this one is the other one which we expect for the last procedure of the construction. We say this distance is equivalent to the amount of work because a person has to finish up the first task to go to the second one, and that distance means just the color distance. And the ratio between the distance and time required to convert this task is the rate of color evolution, or it's more like color-based productivity. After we are done with the first step, the second step continues. I mean, it involves point cloud filtering and processing. I mean, it's kind of a usual procedure. We use the moving least square method to filter it, and we kind of put it in partition cubes as if using in octree partitioning methods. Once they are segmented, then we go to the second color quantity extraction, which is it's almost pretty much the same as what we had initially. So every time we get the points, also this is the short column that we have in the lab, we get the central point as well, and then it will be useful to compare the distance between each steps. Now this is the final one. From this, what you see is, so the black dots represent the as-planned points, the color dots represent the as-built points. We expect them to be aligned together, but that doesn't happen. It's just because construction, the environment in construction is not really fixed. So we need to have an error limitation or acceptable error distance. And we worked on that, but after we plotted, we saw that, okay, these 3 points are actually shifted in the same direction from the planned one. So there must be some kind of calibration mechanism. And for that, it's under more work. But for this one, we work on this one. So we magnified this and we did this. So the acceptable limit, we calculated an acceptable radius from the as-planned point center using just this one standard deviation from the A and B color coordinate points. And if the distance between these 2 points is within the acceptable limit, then we say, okay, that we can take it and we can move on to the next one. However, this is not telling us if exactly if the system is, the construction is actually delayed or is on time. Therefore, we came up with this generalization. R represents the rate of color change, AP is for as-planned, and AB is for as-built. If these relations are found, then we can generalize the construction or the task as delayed, or if it's okay or ahead of time. However, this is kind of complicated. We put it on the usual format, which is the EVM format and value method. As I said earlier, we are kind of equating color distance with amount of work. So we put color distance here instead of cost, and we kind of able to calculate the work variance and the delay from this plot. This is all about the research. To summarize what we have done throughout, we enrich the B model using a specialized database which is called the point center. Then after we filter the point cloud. When we filter it and when we segment it, we enhance those two usual methods because we don't want to over-approximate the points. When, for example, if you are going to do filtering, you are going to approximate points and get a surface points which are not actually the real points that are collected on site. So we need color entities to be attached to those points. So we use the real ones which are actually on a close proximity to the approximated. Productivity ratio is calculated depending on the color characteristics. And the third one is we kind of successfully, I would say, related schedule work and trade using the color property of a material. Well, that's all. Thank you very much.